It glows, not with sunlight, not with warmth, a thin blue skin of haze, wrapped around a world so far from the sun that daylight there is 1,000 times fainter than on Earth. For decades, nobody knew it was watching back. 185 miles up. Layer after layer of it, stacked like smoke frozen mid-drift, circling a body most people had written off as a dead rock at the edge of the map. It shouldn't glow the way it does, it shouldn't be cold the way it is, and for nearly 10 years, no instrument on Earth or in orbit was sensitive enough to prove what a small group of scientists suspected, that this haze wasn't just decoration, it was running the whole show. This is the real story of Pluto's haze, and the telescope that finally caught it in the act. Stay with me. By the end of this, you'll understand why a haze thinner than cigarette smoke may be the reason Pluto's atmosphere behaves like nothing else in the solar system, and why that same haze might explain how life got started on Earth. The flyby that changed everything, July 14, 2015. NASA's New Horizons spacecraft, after a 9-year, 3 billion-mile journey, screamed past Pluto at more than 30,000 miles an hour. It had one shot, no braking, no orbit, no second pass, just a few hours of close contact before it hurtled on into the dark. What it sent back rewrote the textbooks. Pluto wasn't a frozen, cratered leftover. It had mountains of water ice, some rising over 11,000 feet. It had a heart-shaped plain of nitrogen so smooth it looked poured, not formed. It had glaciers in motion, flowing across the surface the way ice sheets flow on Earth, just made of frozen nitrogen instead of frozen water. Every one of those findings landed on front pages within days. The dwarf planet demoted 9 years earlier suddenly looked more geologically alive than most of the solar system's larger worlds. And above all of it, something nobody had modeled correctly, a haze, not a thin veil. A structured, multi-layered blue shroud visible in more than a dozen distinct bands, climbing over 300 kilometers above the surface, nearly 20 times higher than Earth's stratospheric hazes reach relative to their planet's size. Scientists had predicted a haze, they had not predicted this one. The images came back in blue and gray, backlit by the sun, as New Horizons looked over its shoulder on the way out. And in that backlit glow, the haze wasn't one smooth layer. It was dozens. Distinct bands, stacked on top of each other like sediment, each one thin enough to be measured in kilometers, together forming a structure with more internal organization than anyone's atmospheric models had room for. Nobody could yet explain why a world with an atmosphere this thin, thousands of times thinner than Earth's, could sustain haze layering that intricate. On Earth, that kind of stratified structure usually requires strong convection, temperature gradients, wind shear. Pluto has almost none of that. Its atmosphere is so tenuous that surface pressure is measured in millionths of what we feel at sea level. And yet there it was, layer after layer, hanging in near-perfect order, around a world that shouldn't have had the atmospheric muscle to organize it that way. Hand, the numbers that didn't add up. Here's where it gets strange. Pluto's upper atmosphere sits at around minus 333 degrees Fahrenheit. That's roughly 30 degrees colder than the model said it should be. 30 degrees, on a world already colder than almost anywhere humans can directly measure. An error that size doesn't happen by accident in atmospheric physics. Something was pulling heat out of that atmosphere far more efficiently than nitrogen and methane gas alone could explain. For over a year after the flyby, that 30-degree gap sat unresolved, a quiet anomaly filed away, waiting for someone to explain it. The first sign, a 2017 hypothesis. In 2017, a young planetary scientist named Shi Zhang, then finishing his work that would carry him to the University of California, Santa Cruz, proposed something unconventional. What if the haze wasn't just floating there? What if it was actively refrigerating the atmosphere? His models suggested the haze particles, complex organic molecules cooked up when sunlight breaks apart methane and nitrogen, were absorbing solar energy by day, then radiating it back into space as infrared heat by night. A planetary-scale heat pump made of smog. If Zhang was right, the haze should glow faintly in specific infrared wavelengths, not visible to human eyes, not something Hubble could resolve. It would take an instrument built specifically to catch heat this faint, coming from a world this far away. That instrument didn't exist yet. Zhang published the idea anyway. Then he waited. Maud. Anomaly 2, the Charon problem. Here's the complication that stalled everyone for years. Pluto has a large companion moon, Charon, orbiting so close that the two bodies are locked facing each other, never rotating out of view. From a distance, their thermal signatures blur into one smeared signal. Every telescope that tried to isolate Pluto's mid-infrared glow ran into the same wall. You'd get a reading, but you could never be sure how much of it belonged to Pluto's haze and how much belonged to Charon's icy crust radiating heat of its own. For years, this meant Zhang's prediction sat untestable, not disproven, just stuck, waiting on hardware that didn't exist. Then, on Christmas Day 2021, it launched. The telescope built to answer the question. The James Webb Space Telescope reached orbit that morning, folding out its golden mirrors over the following weeks, beginning a slow calibration that would take most of 2022. Webb had not been designed with Pluto's haze in mind. Its primary mission was aimed at the deep universe, the first galaxies, the earliest starlight, atmospheres of planets orbiting other suns entirely, but its instruments happened to be sensitive enough, in the right wavelengths, to do something no purpose-built planetary mission ever could: read the faint infrared breath of a world 3 billion miles away and separate it from the glow of its neighbor. By the time it turned its mid-infrared instrument, MIRI, toward Pluto, JWST carried something no previous observatory had: the resolving power to separate two overlapping heat signatures 3 billion miles away. Researchers led by Tanguy Bertrand, an astronomer at the Paris Observatory, aimed MIRI at the Pluto-Charon system and captured thermal light curves at 4 distinct wavelengths: 15, 18, 21, and 25 micrometers. For the first time, Pluto's heat signal and Charon's heat signal came apart cleanly. Then, in a follow-up campaign, JWST captured something even more valuable: a full mid-infrared spectrum of Pluto's atmosphere, spanning nearly 5 to 28 micrometers, a spectral range no instrument before it had been sensitive enough to read. What the spectrum revealed. The data matched Zhang's 8-year-old prediction almost exactly. Pluto's haze was glowing in the infrared, radiating heat back into space precisely the way the 2017 model said it would. The mechanism wasn't theoretical anymore, it was measured. In planetary science, it's not common to have a hypothesis confirmed so quickly within just a few years, Zhang would later say of the result. We feel pretty lucky and very excited. The findings were published April 2025 in Astronomy and Astrophysics, with a fuller analysis following June 2, 2025 in Nature Astronomy. 2 papers, months apart, converging on the same conclusion from 2 directions. Pluto's haze isn't a side effect of its atmosphere, it is the climate system. Anomaly 3. Something is leaving Pluto entirely. But the haze data wasn't the only surprise buried in the observations. The same campaigns picked up evidence that material from Pluto's atmosphere, volatile ices, seasonal deposits, was cycling across the surface in patterns tied to Pluto's 248-year orbit around the Sun. And more strikingly, some of what escapes Pluto's thin atmosphere doesn't stay in Pluto's system at all. It drifts. It settles on Charon's poles. 2 separate worlds, gravitationally locked, quietly exchanging atmosphere across empty space, one bleeding gas, the other collecting it as a dark, reddish residue at its northern and southern caps. Picture what that actually means. Charon has essentially no atmosphere of its own to speak of. It is a bare, icy moon, tidally locked so tightly to Pluto that the two always show each other the same face, orbiting a shared center of gravity like 2 dancers who never break their grip. And drifting across that gap, invisible and constant, is a slow rain of methane molecules, escaping Pluto's weak gravity, crossing tens of thousands of kilometers of vacuum, and settling permanently onto Charon's poles, where sunlight and radiation convert them into the dark, reddish material astronomers have puzzled over since the 2015 flyby first photographed it. Nowhere else in the solar system does this happen quite this way. The bigger theory. This is where Bertrand's team pushed the implications further than Pluto alone. If a thin, cold haze can regulate an entire planetary climate through radiative cooling, the same mechanism could be at work on other hazy worlds scientists have struggled to model correctly. Neptune's captured moon Triton and Saturn's giant moon Titan, both known for atmospheres wrapped in orange or blue smog layers of their own. This is unique in the solar system, Bertrand said of the finding. It's a new kind of climate, let's say. And then the idea goes further still, all the way back to Earth, billions of years before oxygen existed here. Before photosynthesis filled our sky with breathable air, early Earth's atmosphere was dominated by nitrogen and methane, the same raw ingredients that build Pluto's haze today. If organic haze particles once blanketed our planet the way they blanket Pluto now, they may have helped stabilize early temperatures long enough for the first chemistry of life to take hold. Zhang put it plainly, studying Pluto's haze might reveal the conditions that made early Earth habitable in the first place. That is a striking claim, a dwarf planet at the edge of the solar system, offering a window into the origins of life on this one. Grounding the claim. It's worth pausing here because claims like this can run ahead of the evidence. Nobody is saying Pluto's atmosphere is a perfect twin of ancient Earth's. The chemistry, temperature, and gravity are wildly different. Pluto's haze forms in an environment roughly 200 degrees colder than anything early Earth experienced, under a fraction of the sunlight, with a much thinner atmosphere held on by much weaker gravity. What the researchers are proposing is narrower and more defensible, not that Pluto looked like early Earth, but that the physical principle, organic haze particles cooling an atmosphere by absorbing and re-radiating sunlight, may be a general rule that applies anywhere the right ingredients are present. Titan, Triton, possibly early Earth, possibly worlds we haven't looked at yet. That's a testable idea, not a proven fact, and the researchers themselves frame it that way. The confirmed result is the haze cooling mechanism on Pluto. The Earth connection is a hypothesis for future study, built on a real, published result, not a leap past it. That distinction matters. It's also, honestly, the more interesting version of the story. Real science rarely hands you a closed case. It hands you a confirmed mechanism and a much bigger question standing right behind it. It's also worth noting what this discovery does not do. It does not resolve the long-running debate over whether Pluto should count as a planet. That argument, settled administratively by the International Astronomical Union in 2006, has nothing to do with atmospheric chemistry and everything to do with definitions. It does not mean Titan or Triton will turn out to behave identically. Each of those moons has its own gravity, its own chemistry, its own distance from the Sun, and each will need its own dedicated observations before anyone can say the haze cooling mechanism applies there too. What the Pluto result does is much narrower and, for that reason, much more solid. It confirms with direct measurement that organic haze can regulate a planetary atmosphere's temperature at a scale and precision nobody had verified before. Why 9 years passed before anyone could check? Consider what actually had to happen here. A spacecraft had to fly past Pluto once, get one look, and send back enough data to notice an anomaly. A scientist had to propose an explanation nobody could test yet. A $4 billion telescope had to launch, unfold, and calibrate for the better part of a year. And then finally, in a handful of observing sessions across 2022, that telescope had to succeed at a task specifically hard enough that no previous instrument could manage it, separating the heat of two worlds locked in a gravitational embrace 3 billion miles from Earth. 9 years, from flyby to confirmation. That is not a fast pace by human standards. It is a blistering pace by the standards of planetary science, where hypotheses often wait decades, sometimes longer than a scientist's career, before the right instrument comes along to test them. Zhang got his answer within a working lifetime. Most don't. Consider, too, everything that had to go right along the way. The New Horizons trajectory had to be calculated precisely enough, 9 years in advance, to thread a single flyby through billions of miles of empty space with no chance for correction. Webb's mirrors, 18 hexagonal segments folded like origami for launch, had to unfurl in the vacuum of space without a single misalignment, because there would be no repair mission if something jammed. And 2 independent research teams, working an ocean apart, had to arrive at compatible conclusions from the same raw data, publishing months apart in 2 different journals, before anyone could call the result confirmed rather than merely suggestive. The question left behind. So where does this leave us? A dwarf planet, stripped of its planetary status in 2006, demoted in the public imagination to an afterthought at the solar system's edge, has just handed astronomers a confirmed climate mechanism unlike anything measured before. A haze thin enough to be invisible to the naked eye is doing the work of a planetary thermostat, absorbing and releasing heat with enough precision that a prediction made in 2017 came true down to the wavelength. And tucked inside that same data is a quieter, stranger detail. Atmosphere leaving one world and settling permanently on another, an exchange happening in total silence hundreds of millions of miles from anyone watching. If a mechanism like this can shape climate on a world this cold, this distant, this seemingly simple, the question worth sitting with is not just what else it explains out there, it's what else it might have already explained back here, in the earliest chapters of our own planet's story, before there was anyone around yet to notice. If you want to go deeper into what Titan's haze and Triton's captured atmosphere might reveal next, that's a story for another time.